All right, so it is our pleasure to have Rafael Pass present the third talk of this workshop, which is all about highlighting some of the most exciting work that's going on in cryptography. And this certainly counts, and you just can't wait to hear more about his exciting work on the foundations of cryptography. Rafael, please take it away.
Thank you so much, Amit, and thank you so much to organizers for inviting me. It's a great pleasure to tell you about this work together with my student Yanyi Liu about the possibility of basing cryptography on X not equal to BP. So let me, before I give you the background, let me just summarize what this talk will be about in one slide. So in a nutshell, what we'll show is that 1V functions, which is really the most fundamental cryptographic building block, exist if and only if a certain problem, the MKTP problem, is hard on average. On the other hand, we will also show that if this problem is hard on average, that is actually equivalent to X not equal to BPP. So this basically almost shows the existence of 1V functions on the assumption that X is not equal to BPP. The only little caveat here is that the notion of average case hardness that we require for both these two results are somewhat different. In particular, in the first result, we require a notion of two-sided error average case hardness, whereas in the second result, we require a notion of errorless average case hardness. But except for that seemingly minor difference between the notion of average case hardness,
and this notion of error is with respect to the input to the distribution, like the input to the
I will go into much more detail about what error is, but yes, indeed, it is with respect to the input. Yeah. So on a high level, really what this result will say then that the only gap between basing 1V functions on X not equal to BPP is this seemingly minor gap in this notion of average case hardness. And these are really two standard notions of average case hardness used in the literature. All right, so that is the kind of preview of everything we will go over, and now let me go over it in detail. So let me start off with cryptography, and let me start by summarizing cryptography in the last 2,000 years. So basically, the way cryptography is proceeded in the last 2,000 years was in what I refer to as the dark ages of cryptography, where crypto mostly was an art. We had an artist who invented a scheme. That scheme was deployed, eventually got broken, and eventually we had to patch the scheme or invent a new scheme, and we were in this cat and mouse game. And that's the way crypto proceeded until the 70s, 1976, when Diffie-Hellman came up with this notion of a 1V function. So 1V function, roughly speaking, is a function that's easy to compute, but it's supposed to be hard to invert it. In a little bit more detail, we require that no probabilistic polynomial time algorithm can, given f of x, recover some pre-image x. The most classic example of a 1V function is, or 1V function candidate, is multiplication. So multiplying large random primes is easy, but if I ask you to factor the product of two random primes, we believe that this is hard. Now, Diffie-Hellman, when they came up with this notion, they kind of intuitively felt that this notion should capture a minimal notion of hardness required for cryptography. And perhaps surprisingly, over the next few decades, their vision really played out. And it was shown that 1V functions are not only necessary, but are also sufficient for most of the basic tasks that we require in cryptography, such as private key encryption, pseudorandom generators, digital signatures, authentication schemes, pseudorandom functions, and so on and so forth. So really, most of the kind of central primitives that we rely on in cryptography, 1V functions are necessary and also sufficient for getting them. These results are very complicated and beautiful and really fundamental results, and proving sufficiency is very non-trivial, but it took several decades to do it. But we now know that 1V functions really are enough for building up a lot of the foundations of cryptography. So it's safe to say that the question of whether one-way functions exist is the most important problem in cryptography. Now, I should point out that one-way functions are enough for what we refer today to as mini-crypt. So these are kind of the basic cryptographic primitives, but there are many more advanced ones, such as public encryption, oblivious transfer, or obfuscation that you heard about this morning. They're not only implied by just one-way functions, and we require additional assumptions to get them today. But the focus of the talk today is going to be on this most basic building block of one-way functions. So whereas the foundations of cryptography starting for one-way function is really beautifully developed and really is developed in a very scientific way where we can get provably secure constructions of all these primitives based on one-way functions. When it comes to constructions of one-way functions, we have a lot less of scientific foundation. And here we're mostly relying on candidate constructions, such as multiplication, as I mentioned, which is the foundation of this factoring based one-way function, the discrete logarithm problem, various lattice problems, or more heuristic candidates like DS, SHA, or AS, and so on and so forth. So far, none of these classic candidates have not been broken. But as Sylvie McCulley said in the 80s, cryptographers seldom sleep well at night. And it's not only because we have conferences late at night, but mostly because it could be the case that we wake up one morning and there's a factoring algorithm that has been developed, and then a lot of the things that we're doing on the internet need to be revisited. And maybe then lattice problems will get broken, and soon thereafter we're out of a job. So it would be great if we could find some problem, and indeed, if quantum computers are built, then, as we know now by Shor's beautiful algorithm, both the factor and discrete logarithm problem can actually be broken. All right, so have we really escaped from this crypto cycle when it comes to these underlying assumptions that underlie one-way functions? So central problem was whether there exists a natural average case hard problem that characterizes the existence of one-way functions. It's a problem that has a property that if that problem actually is hard, then the one-way functions exist. And if that problem is easy, then no one-way functions can ever exist. If we had such a problem, we could focus all our attention trying to break that problem. And if nobody managed to break that problem, then we have very good confidence that that one-way functions exist. So a few years ago, or 2 years ago, a little bit less than 2 years ago, in I think last year's Fox, together with Yanni, we showed the existence of such a natural problem. In particular, we showed that the T-bounded Kolmogorov complexity problem, the average case hardness of that problem is equivalent to the existence of one-way functions. In more detail, for every polynomial T greater than, let's say, 1.1n, one-way functions exist if and only if the T-bounded Kolmogorov complexity problem is mildly harder than average. So at this point, I haven't told you what this problem is, and I'll do so shortly. But before going into what Kolmogorov complexity is, and in particular T-bounded Kolmogorov complexity problem, let me introduce what I'm going to talk about today, which is a new result, a follow-up result to this LP20 result that asks the question of, can we weaken further the assumption on which we can get one-way functions? And when I ask about whether we can weaken it, I'm ideally looking for some very, very weak assumption about feasible computation. And perhaps the weakest, it's not, one can conceive of even weaker ones, but an extremely weak and reasonable assumption is the assumption X is not inside BPP. So what does this assumption mean? So as you know, X denotes a set of languages decidable in exponential time. And BPP decides the set of languages decidable in randomized polynomial time with two-sided error. So we strongly believe that X is not equal to BPP, but embarrassingly, this has not been proven. So we can think of this assumption that X is not inside BPP or X not equal to BPP as saying, roughly speaking, that randomness does not exponentially speed up computations. Now, that's an extremely reasonable assumption, and basically, if there's any justice in the world, one would think that just tossing a few random coins should not allow us to exponentially speed up computation, right? That would just be crazy if we could exponentially speed up computation randomness. Now, if these type of justice-based arguments are not enough to influence you, suffices to say that there are our two favorite believable assumptions in cryptography or in complexity theory also imply this assumption that X is not equal to BPP. In particular, if NP is not inside BPP, then since NP is inside X, we also trivially have that XP is not equal to BPP. And if BPP is equal to P, or in fact, even if BPP is in sub-exponential time, then since we know that exponential time is not in sub-exponential time, we also directly get the assumption that X is not equal to BPP. So this really is a super kind of minimal assumption implied by NP not inside BPP and implied by, as we said, BPP inside sub-X. And just on a personal level, it just seems, would seem crazy if random was allowed to speed up computation exponentially. Okay, so what are we doing this work? What we're looking at is the question of whether the assumption that X not inside or not equal to BPP, what is required to go from this assumption to this pretty strong assumption of the existence of one functions. So what is required to take us from kind of the minimal assumption into something that's a pretty strong assumption and which suffices for most basic cryptography. And now we can go back to the first slide of the talk. In particular, what we show is that there is this Kolmogorov complexity problem, such that average case hardness of this problem with respect to two-sided error heuristics is equivalent to one functions. And average case hardness of this MKTP problem with respect to errorless heuristics, on the other hand, is equivalent to X not equal to BPP. And therefore, the only gap to go from here to here, and in fact, the exact gap to go from here to here, is going from errorless heuristics or to hardness with respect to errorless heuristics to hardness with respect to two-sided error heuristics for this particular problem. Okay, so at this point, I have to tell you about what this Kolmogorov complexity problem is. Actually, sorry. Before doing that, let me formalize this result in a little bit more detail. And what is going to be required here is actually to formalize the notion of one function. So first, the notion of one function, as you probably are aware of, we said that one function is a function is one way if the function is efficiently computable, and it is the case for every probabilistic polynomial algorithm A. There exists a negligible function such that this algorithm A can only succeed in inverting the function f with negligible probability. Now, in crypto, we typically require the attacker to fail on all input lengths. So A should succeed in doing this with negligible probability for all input lengths. There's also a more complex theoretic notion of one function called an infinitely often one function, where instead of requiring this result for all, we instead require it to be the case that A fails on infinitely many input lengths. The focus of our talk today will actually be on these infinitely often one-way functions. Okay, now we're ready to move on to Kolmogorov complexity. So Kolmogorov complexity is a beautiful notion introduced independently by Solomonov, Kolmogorov, and Jain in the 1960s. And it's answering questions of the following type, or it helps us answer questions of the following type. On this slide here, you see two strings, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then the second one, 1, 7, 3, or 5, blah, 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 blah. Which of the following of those two strings is random? Well, clearly the top one here does not look very random at all, whereas the second one clearly looks much more random. So, but how do we make sense of a statement like that? How can we formalize what it means that the top one is less random than the second one? Well, this notion of Kolmogorov complexity allows us to do exactly that. We refer to the Kolmogorov complexity of a string x as the length of the shortest program that outputs the string x. If you look at this string here, the Kolmogorov complexity of that string is pretty small. It's just print 1, 2, 3, and then a for loop. Whereas for this string, presumably there is no shorter program than just printing the whole string, just hard-coding the whole string and printing and writing print that string. So this string will have small Kolmogorov complexity. This string will presumably have large Kolmogorov complexity. So this notion gives a very elegant way of quantifying the amount of randomness in individual strings. Formally, to formalize this notion, we really need to consider some fixed Turing machines. And we're looking at the length of the shortest program, MW, that's such that U of MW outputs the string X. But for now, just forget about that. And you can think of programs in your favorite programming language, like Python, let's say. So this notion has lots of amazing applications. And my favorite one is it's a beautiful proof by Gödel's of Gödel's incompleteness theorem. This was actually one of Chatin's original motivations, but it also has applications in pure maths, such as proving the density of primes, and so on and so forth. Lots of amazing applications. But on the negative side, this notion is not computable. Now, that could be a good thing if you're trying to prove an incompleteness result, but if you're trying to use it to practically measure the amount of randomness in strings, not very useful. And indeed, that was pointed out by Kolmogorov already in his original paper. And this notion of time-bounded Kolmogorov complexity was considered in order to circumvent this problem. So the time-bounded or T-time-bounded Kolmogorov complexity of string X is simply the length of the shortest program outputs the string X within some fixed time bound, T of length of X. And here you should think of the time bound as being some polynomial. So now we can again ask, can KT, where T is a polynomial, be efficiently computed? And this is a problem that's been studied since the 1960s in the Soviet Union and came to the Western world around the 80s. It's closely related to something called the minimum circuit size problem, and more generally falls within an area called meta complexity. And it was with respect to this particular problem that we proved this result that I mentioned a few slides ago, that one-way functions exist if and only if the T-bounded Kolmogorov complexity problem is mildly hard on average. Any questions?
Can you similarly use the minimum circuit complexity problem? Is there like a variation of this that could work?
Yeah, there are some. I won't have time to go into that now, but unfortunately, we don't know how to get this equivalence with the MCSP problem for various technical, kind of annoying reasons that make Turing machines easier to work with. I'm happy to tell you more afterwards.
Sounds good.
All right, so now we're going to move on to this other notion, the MKTP notion that I mentioned, which refers to a different notion of time-bounded Kolmogorov complexity. So this is a notion that was introduced by Levin in 1973. And Levin had this complaint about the notion time-bound component complexity. So if you go back to this notion and look at it here, the issue here is that this notion is very strict when it comes to time bound. Like if your program exceeds this time bound by one step, it becomes illegal, right? So it becomes very non-continuous, perhaps. Another issue with this notion is that it's very, very tightly tied to the underlying universal Turing machine or programming language. If you switch to different programming language, then the running time might change by a little bit, and then suddenly you might exceed the time bound. So it seems like something non-robust about notion. Also, another ugly aspect of it is that you need to have this time bound there. It's parameterized by time bound. Now, in our results here, we can show it for every time bound, but you know, when you want to consider the problem of efficiently computing this Kolmogorov complexity, time bound, which time bound should we pick? Should pick n squared seems reasonable, but why not like n to the power of 1.5? You know, which t should we pick? So Levin introduced this other beautiful notion where he said, let's look at the cost of the cheapest program that outputs string x. Okay, so now I just need to define cost. So in normal Kolmogorov complexity, the cost is just the length of the program. We don't care about running time. Okay, so Levin suggests that maybe what we should look at is the sum of the length of the program and the logarithm of the running time of the program. Okay, so that's what we're going to refer to as k little t. So there's no t above, now just the t is kt. And the MKTP problem refers to pairs of strings x and a threshold such that the Kolmogorov complexity of x is less than the threshold k. So this is a decisional problem. Now, the first note, why do we charge logarithmically? Well, the intuition that Levin had was that we'd like to capture the idea that polynomial time computations are cheap, right? But exponential time computations should actually induce a lot of extra costs. So any, like, you know, increasing the runtime by some polynomial only adds some small logarithmic term. So that doesn't really change the Kolmogorov complexity by a lot. But if you start running by more, then now suddenly you're going to pay a large price. So that's super elegant, no longer a time bound. It's a much more robust notion. There is one slight problem though. This notion is computable, sure, but it's no longer inside NP, whereas time-bound Kolmogorov complexity is inside NP. And the reason it's probably not in NP is because you could have a statement X whose witness is a program. So remember, a witness here is going to be a program that outputs a string X, but the running time, maybe the program is of length n/4, but the running time could be of, let's say, 2 to the n/4. So the running time could actually be very large for the program that minimizes the sum of the length and logarithm of runtime. And therefore we cannot check whether this indeed is a valid witness. So that's just kind of some intuition why it might not be an NP. Even more strong evidence of this is a beautiful result by Aller et al. That showed that actually the MKTP is X complete under P/poly reduction. So what that means is that X not inside P/poly implies that MKTP is not inside P/poly also. So unless we think that X is equal to NP, this is not going to be complete. Okay, so now I've told you the problem we're going to look at. Now I also need to go over in more detail two notions of average case hardness. So as I mentioned, there are two quite different notions of average case hardness studied in literature. And I'm going to start with the one that's most commonly used in cryptography. So let's start by considering what it means for a problem, a language to have an average case heuristic with a two-sided error. So we said a language L has a deterministic heuristic. I'm going to start to defining things for heuristic P, where the actual algorithm is deterministic. If there exists an algorithm that is able to decide this language with probability 1 minus 1 over poly for every polynomial. Okay, in other words, for every polynomial, there exists a deterministic algorithm H such that over random statement X, and for now, I'm going to assume that this is over uniform. In fact, all throughout the talk, I'm going to just assume when I pick a random statement X, it's a uniform random string of length n. The probability that this heuristic does not correctly decide the language is less than 1 over p of n. Is everybody with me? This notion, this is the most basic and simple notion. Okay, excellent. So now let's move on to another notion that's maybe more popular in the complexity theoretic literature, which talks about errorless heuristics. So we say that a problem is in average P if for every polynomial there exists a deterministic heuristic H. Now this heuristic, in fact, shouldn't just try to compute what this language is. It is required to never ever make any mistakes. Okay, it can give up, it can say I don't know, but once it gives an answer, it better give the right answer. So required for every string X, this heuristic can either provide the right answer or give up and say, look, I don't know, this one I cannot decide, I cannot be sure, so I give up. Okay, so think of this as you're trying to complete some exam, and if you ever make an incorrect answer, you get 0 on the whole exam, but you're allowed to skip questions, right? So you should, that's like we tell students, don't try to guess the answer, only provide the answer if you know how to do it. So that's the difference between errorless heuristics and two-sided heuristics. That's how we want people to be, that's how people are. Okay, so really the difference here is that such a heuristic can be unaware of when we make mistakes. Errorless heuristics, they're allowed to kind of, give up, but they should only give up when they know. They can only make mistakes when they know it. They have to say like, look, I don't know this. I'm not going to commit to. I don't know what the answer is. But okay, and then of course here we require that the probability that we give up should be small. So this is means to have a heuristic that's deterministic. We can also extend this in a straightforward way to consider also randomized heuristics. So in this setting, in the two-sided error setting, we define the class heuristic BPP in exactly the same way, except we will just replace deterministic here to randomized. And now the probability is both of the statement X and the randomness of the heuristic. And in the case of errorless, the definition is essentially also exactly the same. The second condition is exactly the same. The first condition, now in order to capture BPP algorithms, we also allow, we don't require the heuristic to always be correct or bot, but this should only happen with probability 1 minus 1 over p of n. Okay. So now we've defined these two classes of heuristic BPP and average BPP. And really what I want you to remember here is two-sided error average case heuristics. That's what we typically use in cryptography. We just require the heuristic to, it's supposed to succeed in predicting this language with probability 1 minus 1 over poly, but it can make mistakes. It doesn't know when mistakes happen. And this one, same thing, it's supposed to do it, but it can never or only make mistakes. It can whenever it makes mistakes, it should know that it happens. Okay. And here, of course, when I write 1 minus 1 over poly, you can use no BPP application to make this much smaller too. So it's you could write 0.9 here, or 1 minus 2 to the minus n. Okay, and now we're actually ready to fully state the theorem. So what we show here is that theorem one functions exist infinitely often. One functions exist if and only if MKTP is not inside heuristic BPP. And theorem 2 says that X is not equal to BPP if and only if MKTP is not inside average BPP. And recall, this is hardness against errorless heuristics, and this is hardness against two-sided error heuristics. So what we see here then is that whether we can base infinite often functions on X not inside BPP boils down to the seemingly minor technical difference between these two notions of average case hardness. In fact, proving that this implies that is exactly what is needed to base one functions on X not equal to BPP. Because if you can go from here to here, then by this result and this result, you have also proven this implication. So this implication going from here to here is exactly what is needed to base infinite often one functions not equal to BPP. Let me just mention very quickly, we can also characterize normal one functions, but that requires us to consider an almost everyone notion of average case hardness. I won't really go into detail on that. Now, the next question you might ask is, all right, so we reduced going from here to here to this seemingly minor problem. How hard does it actually go from here to here? Well, our next result shows that if you manage to unconditionally show that hardness of average MKTP with respect to errorless heuristics implies hardness with respect to two-sided heuristics, then you have actually also shown that MP is not equal to P unconditionally. So, there are two ways of interpreting this thing. The pessimistic way is that closing this gap is going to be very, very hard. The optimistic way is that, maybe this is a new approach towards showing that MP is not equal to P. Maybe, this gives you some very concrete algorithmic approach. Try to solve MKTP in an errorless way, having access to two-sided error oracle. And if you can do that, then you've also shown not only based one functions on X not equal to BPP, but you've also shown NP not equal to P. Up to you to choose which interpretation you're more inclined to believe. So let me briefly review some related work. So as I already mentioned, this beautiful work by Allen et al. Shown X completeness of MKTP with respect to P/poly reduction. And as I mentioned, what that means is that if X not inside P/poly, that implies that MKTP is not inside P/poly. Note that this is shown MKTP is worst case hard. In contrast, what we want to show is that MKTP is also average case hard. But indeed, this will be a very important starting point for us to get average case hardness, assuming X not equal to BPP. Additionally, as we already mentioned, this previous result that we have showing equivalence of one functions, average case hardness of time and Kolmogorov complexity, and that's also going to be our starting point for showing that one functions are equivalent to two-sided error average case hardness of MKTP. And we finally mentioned that Ren and Santaman have independently also presented an analog of, or actually showed this result independently, and they also presented some analog of this thing, not in terms of X and BPP, but under different assumption. All right, so in the next 10 minutes or so, let me try to very quickly go over on a high level these two theorems. The first result shows one function is equivalent to MKTP not in two-sided error BPP, and the second one of X not equal to BPP if only MKTP is not in errorless average BPP. I have to point out here that all of these proofs in this paper are actually mostly conceptual later, given the previous works. And so really all the heavy lifting happens in these previous works and some other work by Impagliazzo and Vidgerson. So we really view this contribution mostly as conceptual here. So let me briefly go over the first result. And so here, let me start by mentioning that the reason that we get only infinitely often one functions is that this assumption is an infinitely often type of hardness assumption. NKP not being a heuristic BPP, this means that this problem is infinitely often hard. If we instead had changes to an almost everywhere notion of hardness, in particular replacing this by saying MKTP is not an infinitely often heuristic MKTP, then we can also characterize normal one functions. All right, that's just a side note. Okay, so how do we prove this? Well, as usual, when you have an if, you need to prove each of these two directions separately. We're going to today focus on the if direction, so showing that this implies that. The only if direction is more complicated, but in the context of this work, is actually not that complicated because it more or less follows using very similar techniques to LP20. So let me focus on the if direction. So the if direction says, if MKTP is hard for two-sided error, average case hard for two-sided error algorithms, then infinitely often one functions exist. Now, it turns out that we actually don't need to get a real one function. As often is the case in crypto, it turns out that it suffices to get a weaker form of one function, which is something referred to as a weak one function. And this is just a one function such that no PPT algorithm can invert f with probability 1 minus 1 over p of n for some polynomial. So there is no algorithm that can invert it with probability very, very close to 1. And this result by Yao shows that weak one functions imply strong one function. So from now on, we just need to construct a weak one function. And to tell you about our construction, let me first review the LP20 construction and see what goes wrong with that. So remember, this construction was a construction of one function, assuming the hardness of the time bundle Kolmogorov complexity problem. So I have some time band T from this time bundle Kolmogorov complexity problem, and that's given. And a simple observation is the time bundle Kolmogorov complexity of string x is never much more than length of string x plus some constant c. Think of this as the length of writing print. Okay, the function looks the following way. I take my input. I'm going to interpret my input as two parts. The first part is some program pi prime, and the second part is an index. The first part is roughly n bits. The second part is roughly log n bits. So the second thing is an index. What I will do is I'll take this program and I truncate it to just be I bits long, and let pi be the truncation of pi prime to only the first I bits. And then what I will do is I'll run the program, the truncated program now, for t of n steps, and I'll let y denote the output. And then finally, the output of the function is going to be the index and the program y. Now, I don't have that much time, so I won't be able to tell you why this works. But the idea here is that if you have somebody who can invert this function, then you can actually use that that oracle in order to determine the time bundle Kolmogorov complexity of random strings. And the high level idea here is that given a string y, if I would like to determine what the Kolmogorov complexity of that string is, I'm going to feed my oracle y, 1, or 1, y, 2, y, 3, y, and so on, and ask this oracle to invert this function. If it manages to invert it, like when y is 3, that means that I have a program of length 3 that is able to output the string y. Now, this is really just an idea, and this idea doesn't quite work in this the way as described it, because we're actually feeding this attacker the wrong distribution. Y here is a random string when I want to determine the Kolmogorov complexity problem, whereas y as being output by this function is not necessarily a random string. So there is a mismatch, and that's indeed what the problem we solve in LP20, but I'm not going to go into that here. Instead, let me discuss the one-way function that we construct here. Now, first thing we're going to do is going to replace k big T with k little t. So now we're talking about 11 Kolmogorov complexity. And the idea then is to, in order to use the same reduction, we're going to output not just I, the length, but I plus log t, where t is the running time of the program pi. All right, so that's very good. That seems pretty easy. And then intuitively, we could use the same intuition to just enumerate all possible values here and try to hopefully are able to, using the inverter for this function, also be able to compute the time-bound Kolmogorov complexity of a string. There is one more major problem here, that before we had this time-bound t that came from time-bound Kolmogorov complexity problem. But now in Levin's problem, we don't have a time-bound t. Right? This notion is not parameterized by time parameter t. So in order for this function to be well defined, I need to run the program for some fixed polynomial number of steps, because otherwise the function is not going to be polynomial time. But it's not clear what this polynomial should be. Now, so what should we set this t, the cutoff time for the program, to be? And if we set this to be some fixed polynomial, we're getting into the issue that we can only decide MKTP when the instance indeed has a witness where the running time is bounded by this polynomial. But as already mentioned, sometimes the witness actually must have exponential running time. So it seems like to be some. So in a little bit more detail, let's the KT witness of a program or a string X be the program that witnesses to the KT complexity of the string. In particular, it's a program that generates X in T steps while minimizing this length of pi plus log T. And as mentioned, sometimes the KT witness could just be a program that runs exponential long running time. Now, the key observation that we show here is that actually most strings turn out to have a KT witness with small running time. And therefore, this construction can be made to work by setting T to be sufficiently large. In particular, it will suffice to decide MKT only for those strings. So the lemma we show is that, in fact, for every n to the c, at most 1 over n to the c fraction of n strings have a KT witness with running time that's much more than n to the c. I won't go into the proof. It's actually very easy. You can look at it afterwards in slow motion if you just zoom in on this slide. But the point here is that by setting t to be n to the c, we can compute MKTP with probability roughly 1 minus 1 over n to the c, and therefore are able to solve the MKTP problem with a two-sided error algorithm. Let me, in 2 minutes, mention a few words about the second direction here. The second direction actually is quite easy. So we want to show that if X is not equal to BPP, then MKTP is hard for two-sided error algorithms. So there's one trivial direction, okay, that this implies that. I'm not going to go over that. The second here is the more interesting one. If X is not inside BPP, then MKTP is average case hard. And the outline is very straightforward and follows Aller et al. By results of Impagazzo and Vidrison, we know that if X is not inside BPP, then unconditional, or not unconditional, then there exists an inefficient so-called PRG. So this is a PRG and whose running time is sub-exponential, but it only fools polynomial time algorithms. Next, our key lemma is going to show that if you have such an inefficient infinite often PRG, that implies that MKTP is average case hard. So the idea here is that uniform strings have very high Kolmogorov complexity, but pseudorandom strings in the output of PRG, actually turn out to have small Kolmogorov complexity, even if the running time is sub-exponential, because we're only changing logarithmically. So logarithmic of 2 to the n to the nu is also going to be small. So there is a gap between the Kolmogorov complexity here and here. Now that intuitively makes it seem like we can just use a heuristic for this problem to just break the PRG and we're done. But there is a problem. This is a heuristic. It may fail on some inputs. Unfortunately, it turns out that one can reason that if this heuristic is errorless, then it turns out that it's going to work still on pseudorandom strings and on uniform strings. On uniform strings, even a two-sided error heuristic will work. But a two-sided error heuristic might not work on pseudorandom strings because these are very, very sparse, and such a heuristic could fail in all of them. But an errorless heuristic turns out actually is going to have to work also on pseudorandom strings, and it can be used in order to solve this problem. So summing up, what we've shown that this MKTP problem introduced by Levin in the 70s has this amazing character. On the one hand, if you consider errorless average case hardness problem, you get equivalence to the assumption that XP is not inside BP. Whereas if you consider two-sided average case hardness problem, you get instead one functions. The conclusion here is that going from here to here, the only gap is just going from here to here. But proving this application turns out to be not so easy, as it implies empirical DP. And let me just mention in the ending slide here is that this result doesn't come in isolation. This really is a golden time, as you see by the color here, for work at the intersection of crypto and Kolmogorov complexity. There's been a lot of really intriguing results characterizing various different types of one functions log space, NC0, and so on, using Kolmogorov complexity and these beautiful worst case to average case reductions for MP by Hirahara through the lens of Kolmogorov complexity. And I'm just very excited about this whole research area. Excellent. Thank you so much. And sorry,
no worries. No.
I run over time.
Thanks so much, Rafael. So since we've run a little over time, I think Rafael, can you stop sharing so that Ayush can get going? And I would love to have heard more about this connection to the P versus NP problem for the gap between the two, but I guess I'll have to find another time to ask you that question. So from the very foundations of cryptography with one-way functions, we'll go all the way to sort of the other end of the spectrum now and talk about the assumptions that are necessary for building IO indistinguishability obfuscation. And with that, I will turn it over to Ayush.
Hi, Amit. So by the way, is this screen visible? Can everyone see this?
Yes, it's visible.
Okay, great. So today I'm going to talk about on the power of lattice-free cryptography. So what is this talk going to be about? This talk is going to be about lattices in cryptography. As you all know, lattices have like really revolutionized cryptography over previous 1 or 2 decades. Lattices have elegant mathematical structure. They lead to plausible post-quantum security, and they have these wonderful worst case, average case connections. But not only that, over the past decade or so, we have seen profound applications, some of which had only captured the imagination of cryptographers for a long time. For example, the most famous application that one can think of is fully homomorphic encryption, but there are so many different applications which lattices have been so successful in building. So in this talk, we're going to ask, is the mathematical structure that kind of underpins the hardness assumptions in lattices, is it really essential to building fully homomorphic encryption and all these applications? For instance, can we construct these primitives relying on assumptions which have no known connections to lattices, assumptions which have no known reductions to lattices, assumptions which may plausibly be conjectured to be secure, even in an unfortunate, unlikely event that the lattice-based hardness assumptions end up being broken. So, and this is not just a question that we're asking to hedge our bets in terms of the assumptions we use to build all these primitives. This is actually a foundational question which goes directly in the spirit of cryptography, where what we want to do, we want to understand really what kind of power certain mathematical structures that underpins hardness of various problems what kind of power does that give us in terms of constructions? And this is what we investigate in this work. This is joint work with my brilliant co-authors, Rachel Lin and Amit Sahai. And for the rest of this talk, just interrupt and ask questions right away. Okay, so what are lattices? They are periodic structure over n-dimensional real space. And in technical terms, they are discrete subgroup of the reals, right? The way we generate it is by taking integer linear combination corresponding to a set of linearly independent vectors, and that's just called the basis, which generates the lattice. And the basis, as you know, doesn't even have to be unique. For example, these green kind of vectors, they generate this lattice. Similarly, this orange set of vectors, they also generate the lattice, and they don't even have to be unique. They could be like many, many of them. So these kind of combinatorial structure of lattice have been studied in complexity and cryptography for a very, very long time. And there are broadly two kinds of flavors of problems that are really popular. One of them is the decoding problem or the closest vector problem, wherein what you want to do, you're given a basis and your job, and you're given a point, which is like close by to some lattice point. And your job is to find the nearest possible lattice point to that point. Similarly, there is another kind of variant, which is also very popular, wherein you are given a basis and you want to find the shortest possible non-zero vector that can exist inside the lattice. And both these variants have been studied for a long time. In the worst case, we know today that these problems, the variants of this are also NP-hard, so that they're really, really hard problems. Now, what kind of properties make it extremely useful in cryptography? There are many such properties, but in my opinion, there are broadly two properties which make it really so crypto-friendly. The first property is that when we work with average case distribution over lattices, that's what cryptography does. They work on average case distribution of lattices. Typically, it's possible to sample these lattices along with two kinds of bases. One kind is informally called as the good basis, with respect to which all these problems actually become really, really easy. There's another kind, which is known as informally, in formal terms, they are known as bad bases, with respect to which these problems appear really hard. But it really gives you this dichotomy. With respect to certain information, these problems become really easy. With respect to other kind of information, this becomes really hard. And in lattices just naturally give you this kind of flavor. Okay. Another property which makes lattices extremely useful is just that it's a discrete subgroup which sits right in the space of reals. And so it inherits this norm that comes along with the real, which is the L2 norm, so distances. So lattices come associated with that. And this kind of is beautifully leveraged, these two properties, in order to construct variety of applications. Perhaps the most famous one is the homomorphic encryption. And I'm going to give you just the structural overview or the structural observations of how a typical homomorphic encryption looks like. This is not going to be anything formal. So in homomorphic encryption, what one does, one just samples lattices from some distribution and samples it along with two kinds of bases. One that I was mentioning, a bad basis and a good basis. Now the bad basis is going to be revealed to everyone. Okay, it lets you sample points from the lattice and it's going to be given to everyone, and that is from the public key. The good basis is typically kept secret, and it behaves as a secret key, and it's going to be used for certain decoding purposes. Now, when you want to encrypt, in homomorphic encryptions, typically the ciphertext actually are points which correspond to points which are not exactly on the lattice, but they are nearby lattice points. So for example, the figure that I'm showing you demonstrates that it's going to be really close to some lattice point. If you want to encrypt a message M, what one has to do, typically just sample a lattice point and then in a noisy way, generate a point that's near to it, where the distance vector, the distance from the point to that point encodes the message somehow. Now it's because of this L2 norm property, what one can do, simply homomorphically evaluate in some way, which is allowed by the schemes. You can evaluate it And the point is, because of this L2 geometry, the structure is not destroyed at all. Like when you evaluate, you'll still get points which are close to the lattice. And now the distance vector from the nearest lattice points actually encodes this value, the function that you want to compute. Now, if you have the secret key, you can do this decoding and get the output. The security really rests upon the fact that you have a bad basis, which is the public key. You can tell whether a point is close to the lattice or it was completely random point chosen from the entire space. And that's it. That's really the structure of how these homomorphic encryption schemes look like. And this is not just homomorphic encryption. This kind of arises all the time in cryptography. The state of art in these constructions is that today you can base these constructions solely upon the security of the learning with error problem, which is a very famous problem introduced by Regev in 2005. It also enjoys worst case connection. So we know that for the best possible instantiation of LWE for homomorphic encryption, you can kind of base security on the worst case problem of gap SVP with the ratio of n squared, which is really amazing. So in this talk, what we want to ask is this kind of structure, is it really essential if you want to build homomorphic encryption and a variety of primitives that follow from lattices and LWE? So in order to formalize that, let's think of the lattice problem that we want to compare it with to be this version of LWE. We're not going to talk about any other lattice problem, just think of it as LWE. And I want to ask, can you give me FHE and other primitives from assumptions which do not have currently known reductions to LWE? In particular, it's that we should plausibly be able to conjecture security even in this scenario that LWE gets broken. Okay. Now it might happen, whatever assumptions we use and build these primitives, it might happen one day that these we might be able to figure out reductions to LWE, which will be amazing. But all I'm asking is that as of now, whatever assumptions I pick should not have any known reductions to LWE. So that's the question. Hopefully that's clear. Now, how do you even approach such a question? There's one way in which what we can do, we can simply find out all the assumptions that we typically study in cryptography and identify which ones currently don't have any reductions to LWE. We can identify that. We can identify similarly all the primitives that we want to build and go for them one by one. Just try building them one by one. That's not the approach that we follow in this work. What we do is that we go for a really strong primitive, which is so strong that it not only implies these primitives, but implies almost all known primitives that exist out there today. We actually build indistinguishability obfuscator, and we show that you can build indistinguishability obfuscator relying on simultaneous hardness, meaning we'll assume 3 assumptions, and we require that all of them assumptions hold. And under those assumptions, we actually construct IO. And what's nice about these assumptions is that none of those assumptions have any known connections to LWE. Okay, and I'm going to cover what exactly those assumptions are in next few slides. And FHE simply comes as a gift of simply comes as a corollary of this theorem. It comes for free. You can build FHE if you have IO and a perfectly re-randomizable encryption. One of the assumptions that we make, which is decision linear, already implies perfectly re-randomizable encryption. Therefore, you can build FHE from the same 3 assumptions. But other than that, as I was mentioning, IO is really versatile. We not only build FHE, we build a whole bunch of other primitives. And just to give you a sense, there are lots and lots of applications. This is just like a small subsampling of the kinds of things that you can build from IO. Okay, I'm not going to go into the individual names and all of that. I'm sure all of you are aware that IO is really versatile. So now let's proceed and let's go over the rest of the talk. So what is indistinguishability obfuscator? Maybe before I'll tell you the theorem, I should tell you what is indistinguishability obfuscator. Indistinguishability obfuscator is a really fundamental primitive And what it's asking this basic question. Let's say you have a program, and what you want to do, you want to kind of scramble it in a way that, and you want to do it efficiently in polynomial time, in a way that makes the same program with the same input-output behavior as unintelligible as possible, therefore leaking as minimum information about the implementation details as possible. Now, coming up with the right definition for itself has been a story of its own. But right now, we have what cryptographic community have converged at is that suffices to hide implementation differences, and that is called indistinguishability obfuscation. So here is how we kind of define indistinguishability obfuscation. So let's say you have two programs, pi and lambda. And let's say they satisfy this premise of being functionally equivalent. What does that mean? It means that these two programs have essentially the same input-output behavior, exactly on every input they have the same output. We also place some common sense requirements just for the definition to make sense. We require that the description complexity of these pi and lambda, they should be the same running time, same description size. Okay. So now if input-output behavior is the same, this description size and everything is the same, what could be different? Really, the difference could be the internal workings, how they are actually implemented, they could be totally different. So what Ayush says is that once I obfuscate these two programs using this efficient or polynomial time compiler, I should get two programs, pi tilde and lambda tilde, which are hard to distinguish by a polynomial time address. And just to drive away the point home, pi you can think of as an example, think of it as bubble sort and lambda as selection sort. We know that these two programs are sorting programs, they are essentially doing the same thing. So appropriately paired versions of these two programs, Ayush says, I cannot, if I give you bubble sort, I cannot tell, you cannot tell me for sure whether I really give you an obfuscation of bubble sort or selection sort or completely something else, some other sorting process. Okay. So this is really simple, the definition of IO. Turns out, as I've been saying, it's been really, really useful. And at this time, it may not be clear why is this so useful and like how the proofs typically go. But that's for another day. There are hundreds and hundreds of papers which show how to use IO to build a whole variety of things. Okay, so this is IO. So now let's come directly to our theorem. So in this work, we show that you can build IO from a pretty interesting mix of assumptions. We require simultaneous hardness, meaning we'll have three assumptions and all of them must be hard of three things. One of them, the first one is the learning parity with noise problem, LPN, over large field with an error rate of n to the minus delta for delta greater than 0. So what do these words mean? Let's just take a look at LPN. So in LPN, let's say you have a field ZP, okay, so prime, and let's say there's n, which is the dimension. Now what I do is that I sample a random secret S from ZP to the n at random, and I sample, let's say, large polynomial. How many? Let's say k, which is large polynomial in n, and I sample vectors ai from ZP to the n at random also. Now if I ask you, I'm giving you ai and ai inner product S mod p. Okay. Now I ask you, give me the secret S. Now of course you can solve this really easily because these are just linear equations, and if there are many of them and they're all chosen randomly, with high probability, you can just simply run Gaussian elimination and solve for the secret S. LPN is a problem which is the same problem, except with the following little twist. And the twist is, I'm going to perturb these equations at random. How? I'm going to choose this error EI with very small probability. I'm going to choose it to be random, meaning with probability n to the minus delta, where n is the dimension and delta is some constant between 0 and 1. With very large probability, 1 minus n to the minus delta, I'm going to set to be 0. So most equations are like completely non-noisy, with the very few which is have a random noise and chosen with probability n to the minus delta. Okay, now this is the same problem again. Find S. LPN assumption says that this problem now becomes hard. Now, let's make a few observations. If delta is small, close to 0, the error probability increases, the problem becomes harder and harder. When delta is close to 1, the probability becomes like 1 over n, and at that time, actually, you can show it's polynomial time broken. So that's the whole spectrum. For IO, we actually need a very small value of delta, very close to 0. In fact, we don't use the search version. We use the distinguishing version. So in this, what we want, the problem says, distinguish this tuple versus AI, uniform. Instead of these equations generated this way, UI that sample at uniform. And again, I'm asking the same set of parameters. Okay, so that's really the thing. Now we're using distinguishing, but another observation is that turns out distinguishing is actually no easier than search. Okay, there's a slight loss in security. I'm not going to go over all those details, but there are connections like this. Distinguishing is no easier than search. This has been a really old problem. Actually, it was introduced for the first time in 1994. And the field version actually came in 2009, the one that we're using. And the best running times for this algorithm to date are very close to exponential. The version that we're using, where the constant delta is close to 0, for that, it takes almost exponential time, 2 to the n to the 1 minus delta. Okay, so it's a really beautiful problem. That's our first assumption. Let's move on to our second assumption. Our second assumption is existence of Boolean PRGs in NC0. So what are these? These are also like really basic objects. What you're asking is a length expanding Boolean function, which is a PRG, takes n bits of input, and it outputs n to the 1 plus epsilon bits, where epsilon is arbitrarily small constant greater than 0. So just expanding a little bit. And you want this function to be actually constant depth surface. So every output bit must depend only on a constant number of input bits. And we want this to be a PRG, wherein you want, when I compute the output y by applying g of x at a random x, this should look computationally indistinguishable to a truly random string of bigger length n to the 1 plus epsilon. Okay. And this is also an assumption that has been extensively well studied. It was introduced a long time ago. And it has seen tremendous amount of work. Actually, it's also intricately tied with the notion of random CSPs, which is even more well studied. Okay, and the best known attacks, for PRGs today are also almost exponential for the parameters that we use. So that's our second assumption. And the third assumption we are making is also a really popular assumption. It has to do with elliptic curve cryptography. So it's a pairing-based assumption, which is also really standard, has seen a lot of work. Lots of things have been built from it. I'm not going to go into formal details. It's a number theoretic assumption. Goes back to the days of Weil and Tate, and then Victor Miller. So these are the three assumptions. Additionally, a technical remark, we actually want all these assumptions to be sub-exponentially secure. What does that mean? It means that against polynomial time adversaries, they should only succeed in distinguishing with a probability no more than 2 to the minus lambda to the alpha, where lambda is the security parameter and alpha is some constant greater than 0. Okay, so these are three assumptions. Let's now make some observations about it. Our question was, does any one of them have any known reductions to LWE? The answer is not. We currently do not know of any reductions to LWE. If you could do that, that will be really, really exciting. And we'll have open up rooms to give new algorithms for all of these problems. We don't have any new insight on that, but we can already make some pretty interesting observations. The first observation is that among the three assumptions, it turns out only decision linear assumption is the one that is known to imply public key encryption. The public key encryption, as you know, is an extremely fundamental object. And amongst the three assumptions, only decision linear is known to imply public key encryption. We don't even know if PRGs and LPN can be, for these parameters, can be used to build public key encryption. Okay, And partly this is due to the fact that we know so little about these assumptions, LPN and PRGs. We know very, very few primitives, a handful number of primitives that we can build from PRGs and LPN. And complexity theory, theoretically, we know even lesser. Okay, and perhaps one reason why they are kind of not as well understood as lattices is because if you look at these lattices problems that we typically use in cryptography, they are actually sitting inside the complexity class CoNP. Whereas these problems, we don't even know if they are in these structured classes like CoNP or even the interactive version like CoM. Okay, so that's totally unclear. And what completely amazes me about this work is that these two assumptions, LPN and PRGs and NC0, for which we know so little, for which we can build only a handful number of primitives, suddenly they join forces with bilinear maps and build something as powerful as IO. So I feel this is a really golden opportunity to work on these foundational questions, understanding the power of these assumptions. And this is something I'm really, really excited about. So for the next part of this talk, what we are going to do, we are going to go over these IO constructions, but I'm not going to give you all the intricate details. The actual construction has a number of steps. I'm not going to cover all of that. I'm going to only give you a very high level sketch and kind of just on a high level, tell you what roles each of these three assumptions play. So let's go right into it. So let's say you want to obfuscate a circuit C, and it takes n bits of input, and it outputs 1 bit. Okay. If you can obfuscate a circuit like this, you can obfuscate all circuits because just the difference is this has 1 output bit. You can simply obfuscate circuits that compute individual outputs. Okay. And I'm going to denote this quantity capital N, which is equal to 2 to the n, where n small n is the little n is the input length. Okay. So it turns out if you want to obfuscate a circuit like this, there is one trivial candidate. This may not be really good, but it's the starting point. That candidate is the truth table. We write down all the inputs from 1 through capital N. We write down all the outputs from C of 1 to C of n. Okay, and that's your obfuscation. Of course, it is secure because it's not going to leak anything about the circuit except the input-output behavior, right? Unfortunately, there's a giant problem with that, and the problem is, of course, that the time it takes to compute this is proportional to capital N. So it's like really prohibitive. So on one hand, you have this trivial candidate which takes capital N time to run. Then there is this obfuscation that you want to build, where the time that it takes to obfuscate should ideally be polynomially in C, right? The size of the circuit C should be no more than that. So these two things really appear for the moment. We can ask for a slightly relaxed code. Can I improve the truth table construction even by a little bit? How much? Let's say I just want to shave n to the 0.01 factor in the running time. I want to build an obfuscation where the time it takes is actually n to the 0.99, proportional to that. Okay. Turns out that in beautiful prior work, long line of work, we managed that if we have a scheme which does that, then we can use another assumption that you're using, DLIN. In fact, there's a whole variety of assumptions that you could use. All I care about is one of the three assumptions. So using that, you can boost it all the way to IO. Okay, so this goal suffices. And in the next of the half of the talk, we'll just focus on building this. In fact, we'll focus on something even simpler, just for intuition building. So we'll just worry about ensuring that the size of the obfuscation is small rather than the running time. Okay, we want the size of the obfuscation circuit should be like n to the 0.99. Okay. So now let's ask, what are we looking at? What do we want? We want a non-trivial obfuscator where we take a circuit C and kind of obfuscate into something which is only marginally smaller than the truth table, like n to the 0.9, right? So how should we view such an obfuscation? On a very high level, it's some kind of special encryption of an input like C tilde, where C tilde consists of the circuit C and some randomness. But this encryption is like small. It's like n to the 0.99 inside, right? But it's not just any encryption. It's an encryption which somehow keeps everything hidden about the circuit, except magically for every input X, it lets you learn the functions of the form UX of C tilde, right? For every input X. So this essentially it lets you compute the truth table, but keeps everything else hidden, and it's short, right? So that's one way of saying it. Another way of saying it is that if I can come up with an encryption scheme where I encrypt an input C tilde, which consists of the circuit C and some randomness, and it magically ensures that I learn the truth table, I would be good. That will give you an IO scheme, right? Turns out this is too complex. We haven't really reduced our problem. The point is that these functions UX of C tilde that I'm hoping for, they're too complex. They're essentially running the circuit C on input X, and so they're as complicated as the circuit C itself. So we haven't really reduced the problem. Okay. So what is the right logical step? The right logical step is, can I replace these functions UX of C tilde with something way simpler than that? Can I make them as simple as possible? Turns out I do. And this is where our second assumption, PRGs in NC0, comes into picture. Okay. Like really amazing prior work since Yao, and then like randomized encode, like AIK, and then recent work also. Using that, we can show that if you have PRGs in NC0, you can substantially simplify the functions that you should care about. So if you have PRGs in NC0, let's say they have locality D is some constant, then all you need to do is just concern yourself with functions that are 3D plus 1 local, meaning that for every output, UX of C tilde must only depend on at most 3D plus 1 bits of C tilde. Okay, and as a consequence of that, UX of C tilde will be a 3D plus 1 degree polynomial. Now, it turns out the minimum degree that you can choose, the locality D you can choose is 5. That is for some reasons which I won't go into. Therefore, you can actually instantiate these things as degree 16 polynomials. So as a consequence of PRGs in NC0, what we have is that all I need to do is come up with an encryption which lets me learn specifically chosen degree 16 functions. By specifically chosen, I mean using the theorem that I told you just now. Specifically chosen degree 16 functions of the form UX of C tilde. And these polynomials are really special in that they let you recover the truth table, but they also guarantee that they also guarantee that you can't learn anything else. They'll hide any information beyond the truth table. Okay, so that's good. Now the next logical step is I have managed to reduce the problem. Can I come up with a special encryption scheme? Turns out the answer is not yet, but we already have some hope. So what's the hope? If it so turned out in this hypothetical world that these polynomials were degree 2 functions, degree 2 polynomials mod p for some prime, let's say like this, then we already have machinery which is also developed previously and also recently, which relies on this elliptic curve cryptography assumption, the DLIN assumption, using which you can actually construct such an encryption scheme if these things were degree 2 polynomials. However, as I said, these are not degree 2 polynomials, they are degree 16. So we can't directly use it. So you have to do something about it. And this is where the final assumption, the LPN, comes into play. So what we do, we look at these degree 16 polynomials and somehow replace them effectively with degree 2 polynomials. How do we do that? We take this input C tilde, we pre-process it in another short input, and we come up with another degree 2 set of polynomials on that short input, such that they match exactly with U1 of C tilde through UN of C tilde. Okay, so we effectively replace UX by quadratic functions, and this is where LPN comes into picture. Now, if you're thinking about it, in general, you shouldn't expect this to be true. You shouldn't, just take any arbitrary large degree computation and be able to pre-process it into in a way that it becomes degree 2. You shouldn't expect that to be like really true in practice. So we actually do, I'm cheating a little bit. We don't actually quite do that. There is additional, our pre-processing is slightly more general. It has a public component in the pre-processing, but I'll be really silent about it. I don't want to give you minor details. I just want to give you the high picture. Okay, so this is the problem. Now you have these degree 16 polynomials, and we're going to use LPN to somehow effectively replace its role by degree 2 polynomials. So what we want to do, we want to find another family of polynomials and another input, but a short input, such that in that new input, the degree 2 polynomials exactly compute UX of C2. And we do it in 2 steps. In the first step, I solve this problem not completely, but like only approximately. So what am I going to do? I'm going to find another short input S. I'm going to find another like degree 2 polynomial, such that for most X, it will happen that fx of S will agree to with UX of C2. It will happen only on most inputs, not for everything, not for every input. And this is where we actually use LPN. Now, once we have that, we have already solved the problem, we have almost solved the problem. We somehow need to just solve it fully. This is where we actually use a really elementary idea in hindsight. We find another short input M. We find another degree 2 polynomial, such that when I add it with what I already computed, it suddenly now gives you the right output UX of C2 for every input. Okay, so this is kind of the step 2. Now observe that once you have both step 1 and step 2, the rest of thing is really easy because I have managed to find this polynomial which agrees with this UX of C2. And just as a remark, these S and M actually depends on the input C2 that you want to. It'll depend on C2 in some way. Okay, so that's it. Let's just go right into the first idea. So we just directly apply LPN. Remember, we had this input C tilde, and we want to convert it into a system of polynomials which approximately solve the problem. So we simply encrypt it using LPN. So we sample So we sample a coefficient matrix A for LPN. We sample a short secret, so AS, and then we add a noisy sparse error generated using LPN. And then we add C tilde arranged as a vector, okay? And this will give you a value B. This is a vector, okay? And I compute this. Now, what's the point of computing this? The point is that together, A and B, A, this matrix, and this B, now encrypts C tilde. It's going to hide C tilde. Why? Because decoding C tilde from A and B is hard due to the security of LPN. Okay. Now, why am I doing this? The point is now it's actually encoded with a very small secret S. The dimension of the secret S is way smaller than C tilde. So the secret information to encrypt this is very small. And this somehow plays a role in the process that I was telling you. Okay, so this is how we do it. So remember, what is our goal? We wanted to find polynomials fx, and then another short input S, such that for most input X, fx of S is equal to UX of C tilde, and fx is quadratic. That's what we want to do. So I'm just going to give you the candidate right away, and then I'm going to argue both these properties. The candidate is extremely simple. It's just UX B minus AS. So what's going on? This is the degree 16 polynomial. UX was degree 16, right? Now let's argue the second property first. The point is, if I observe B minus AS is nothing but C tilde plus error from this equation, and I know UX is like extremely simple function. It only depends on 16 bits of the input, and the error is extremely sparse, right? Because of the LPN. And therefore, for most X, what will happen? UX of C tilde plus error will already be UX of C tilde. Because for most X, the inputs that it depends on won't be affected with the error. Okay, so that kind of solves my second problem. What about the first problem? And this is where the size of S comes into picture. Remember, S was very small in dimension, and this is just a degree 16 polynomial in S, right? It's also degree 16 B and A, but we don't care about degree of B and in A because they're public. They are encryptions and they actually don't reveal anything about each other. Okay. So degree essentially is 16 in S, and S is very small. So I can trivially quadratize it in some way. So I can, when I look at the same polynomial in another variable, which is capital S, which consists of all the monomials of S of degree at most 8. In that, it's actually degree 2. And as a consequence, I have found my polynomial. All I need to do now is make sure that the size of S is small. And turns out, just because S is very small, the size of S is also going to be small. Just to give you a sense of parameters, if S was like n to the 0.1, capital S is going to be like n to the 0.8. It's still not too large. Okay, so that summarizes the first part. Now what we have to do, we have to kind of take it all the way to the fully correct output. And this is really elementary, but only in the hindsight. Okay, what we observe is that we've already solved the problem somewhat. So remember, we wanted to compute ux of 1 of c tilde to un of c tilde. We actually computed x. And the difference is actually a sparse vector. It's really sparse. Most of the times it's 0. And there is actually a very easy way to quadratize this function. So the correction function is exactly if we can come up with a function for this. And it's really easy. You kind of arrange it in a matrix and observe that it's going to be a sparse matrix. And then you use matrix factorization to kind of compress it. And that's it. Once you have that, you'll get the other function also. Okay, so this kind of completes the overview of the scheme. And unfortunately, I couldn't go over the details, and it's like infeasible to do that in such little time. But hopefully it's clear where all these assumptions played an important role. PRGs was used to kind of simplify the nature of computation from like large degree to like degree 16 or whatever constant degree. Bilinear maps was to enable us to take like these degree 16 functions and bring it down, down to as close to, like bilinear map actually enabled us to give us a model in which we can handle degree 2 computations. And then LPN came along and helped us to take this degree 16 function and kind of convert it into a low degree function that could have been evaluated by using bilinear maps. So that's like the overall summary. With that, let me end at some really, like there are many open questions of our work, but let me just give you 2, which I'm really excited about. One of the questions I'd really like to see resolved is if we can directly construct a fully homomorphic scheme, fully homomorphic encryption scheme, or other kinds of lattice schemes directly from these assumptions rather than going via the route of file. Okay, and that will give us more and more insight about how you can use the structure underlying these assumptions. Okay, so that's one question I'm really excited about. And then I kind of mentioned all these questions before, but one thing also that really bothers me is like just how limited our understanding is about complexity questions for LPN and PRGs. And can we construct reductions to LWE or lattice problems for any of these assumptions? Now, there's only one example which I'm aware of where LLL is kind of used to attack a number theoretic assumption. And that's variant of RSA when you can use Copernicus method to break kinds of RSA schemes. I wonder if there are such things known for, or if you can do similar things for any of these assumptions. Okay, so I'm really excited about that. And then I've also mentioned, like from LPN PRGs, can you build public encryption? As I said, for these parameters, we don't even know how to build public encryption. And what will also be satisfying if you can actually show that they are inside structured classes like SDK or CoAM or things like that. And with that, I'm happy to take any questions, and thank you very much for listening.
All right. Awesome, Ayush. And let's see, are there any questions that anyone would like to ask? Unfortunately, our first speaker had to go because it's extremely late in Israel right now, which is where he is. But Ayush is here. And I also, of course, know it is the end of this Fox Day. So let's take this opportunity to thank thank both of our speakers again in our minds, and we'll see you all tomorrow.
Thank you so much.